Okay, today we're going to have a little look at the required practical on waves. We've got two little bits of an experiment for you. One is a ripple tank and the other is what's called a standing wave. So this piece of equipment here is called a ripple tank. We can see we've got four legs, a base that supports a clear plastic water container. Here we've got a motor. The motor's got a weight on it, which means that it will make everything vibrate. We can see this where the motor is attached on a string, and you can see the motion of that, which actually will create the wood is just touching the water, and that bouncing up and down is going to create waves in our ripple tank. We've got a light here which is attached to one of our power units to give us a light to be able to see it with, and obviously here is we only need quite a low voltage to be able to get our ripple tank to actually work. But if I show you quickly how that does work, as we turn the voltage up, we can see that on our white piece of paper on the desk here we end up with a patterning. Now obviously that's going far too fast for us to be able to calculate to count the frequency of the waves, and it's also going too fast for us to measure the waves. However, we can slow down a little bit and make it a little bit easier. The trouble is it will just go, it's quite temperamental, so it does go off. So we can end up with something like that. Now if I show you a way of measuring the wavelength and the frequency, what I've done here just on the phone is filmed in slow motion. That obviously paused now. You can see the wavelength is between the two white lines. So we've got there measuring about 12 centimetres to measuring 16 centimetres. So I would say the wavelength there is about 4 centimetres. To calculate the frequency, the best way of doing it would be to film it in slow-mo, and you can film how many times each of those white lines is passing that point over a certain time. I've actually got it just out of shot here, the timer, but for example if we were to time just 1 second on slow-mo, might be a little bit awkward, but maybe we could do 10 seconds of measurement, count how many waves go past a certain fixed point. That's just a pen line on the card, and then obviously divide it by 10 to how many times per second that's happening. But that's just a way of demonstrating how this works. We can see that the frequency, the more voltage I put through there, the frequency will change, it would appear, because they're running really, really fast. And obviously the wavelength, you can see with your eye, is much, much shorter. As we slow it all down, we get a longer wavelength and a slower frequency, I would believe. So that's that part. The other part is this equipment here. So what I've got here, this piece of equipment is called a vibration generator, and what that's going to do is allow us to control sorry, that's the signal generator. This is the vibration generator. The signal generator is powering this little unit, and effectively what that's going to do is pump this piece up and down at a certain speed. What we've got is a clamp stand. We've got a mast just to keep everything balanced. Piece of string runs through there, so it will go up and down as that oscillates. We've got a wooden bridge. The string carries on through, goes over our pulley and hangs down. Now the weight there, the mass there, is to give us a tension in the string. Without there being any tension in the string, we would be struggling to demonstrate what happens. But if I put this on, you'll be able to see. This, by the way, is just a strobe light, which allows us to see potentially the actual wave formed. Now here we can see that we've got a double wave. It would would be possible to calculate the wavelength, but with it being a transverse wave, we might be struggling with regards to the frequency, were it not for the fact that this is obviously, we can see how changing the power on our signal generator will change the wave that's formed. There's a few other things that will change the wave that's formed as well, but if I just show you this, it should go down to one longer wave. I can hear there's a bit of rattling, but you can see that as being one longer wave, the wave being created between the length now of the wooden block and there. We can see with that as it is, altering this will obviously affect, well, what does it affect? It seems to be affecting the amplitude more than anything of our wave. We've got an increased amplitude with a shorter distance. You can adjust the strobe sometimes to get a better measurement. That's just a little bit awkward in some respects. And the other thing we can do to change is change the amount of tension that's in there. You can see that that is creating a different wave again to what we were creating. It's probably easiest to see if I pop that wave back on. We can see the change in the wave. But that gives you the idea of what it is that we're trying to achieve. I think what they're asking you to calculate is literally the wave speed, and the wave speed is simple calculation of multiplying the frequency by the wavelength, which will give you a frequency is obviously in the number per second, and the wavelength you could either be doing in centimetres or in millimetres, and that would give us a speed calculation. So again, hopefully that's been useful. You can see how the kit works. It's quite interesting to have a play around with different bits and pieces just to see how things change and find different patterns and wavelengths. Literally changing the amplitude on here gives us the opportunity of changing the amplitude, and you can see how that's come to a much shallower amplitude, and that's about the maximum. So it just gives us an opportunity of playing around with the kit. You'll hopefully sometime get the opportunity to see how it works, but it gives us a chance to explore how waves work and how they're measured. Hope that's been useful. Thank you.